Yeah, thank you, Adrian, and thank you all for being here and for the kind invitation. It's the first time that I visit CENTRA, so it's a great pleasure. I'll be here today and tomorrow, so if people want to chat more, I'm in the fourth floor, so yeah, the door is open for more discussion. So I'm sure you're all very excited about gravitational waves. To me, one of the major aspects that this new field is gonna do is open up the opportunity to explore new regimes in the universe. And this is, of course, something that comes on top of, like, I guess, a long time of exploration. Exploration since in Denmark, we are very proud of Tycho Brahe, who took a detailed mapping of the solar system that then allowed Kepler to understand the laws of planetary motion. But also, as we enlarge these telescopes, we realized that our notion of the universe was different. And in particular, with Hubble, finding extragalactic sources, and now with our state-of-the-art space telescope that we are seeing galaxies billions of years ago. So I think something that comes with all of these advances in technology is that we have found always surprises. And when we put all of these very different observations of the universe, from the very radiation of the early times in the cosmic microwave background, the observation of explosive events such as supernova, the whole structure of the universe that forms this cosmic wave, and also the fact that light from distant objects is gravitationally lensed, you build this model of cosmology that is actually remarkably simple and explains 13.8 billion years of cosmic history. But of course, as you all know, this model has some fundamental missing pieces, and there are key aspects that we don't really understand, and I think that motivates part of my research, such as why the universe is expanding now every time faster. That's related to dark energy, of course. What holds galaxies together? That's related to dark matter, and in particular, how is the substructure, what is the nature of this component, but also basic questions such as, we assume that gravity, as we understand it in our labs, in our solar system, is valid at the scales which is orders of magnitude bigger. So I think it's also important that we go and test the validity of Einstein gravity through the universe. We are lucky that now we are in a new era of gravitational wave astronomy, where we have detectors throughout Earth that allow us to detect these new cosmic messengers that bring us new information to probe these new regimes of the universe. And as you know, like these systems that we are observing, stellar mass black holes, stellar mass compact objects, most of them are binary black holes that we observe through the period of in-spiral until they get closer, merge, and then ring down. This is, as you know, the strain of the gravitational wave as a function of time. But to me, what is more impressive of this plot is actually the bottom panel. Well, sorry, of course, one of the magnificent results of this plot is the fact that you have here numerical relativity, which comes from this Einstein field equation that were predicted 100 years ago, and you see that they actually very well reproduce what we are observing. So that's a good check for Einstein gravity. But what I was saying is that, to me, I mean, what is impressive is when you look in the bottom panel, the velocity of these compact objects as a function of in units of the speed of light, and also the separation in units of the Schwarzschild radius. You have these tens of solar mass objects moving almost at the speed of light, colliding with each other. And that's equivalent, of course, of talking about strong field gravity, which is something that we are only now starting to probe. But these observations are not only revolutionary for strong field gravity, they are also revolutionary in terms of astrophysics. Because when we think of the possible stellar evolution, many of these evolution paths for the stars, they involve black holes as the end product or neutron stars. So one of the main questions that we as a community try to answer is how, when, and where do these compact objects form? How they form? How can we find them? But there is gravity, there is astrophysics, but I think to me also the very interesting pillar is cosmology. So to exemplify that, you can take the distribution of stellar mass compact binaries as a function of distance, as a function of time. We are here at the center of this diagram, and then the radial direction is the look-back time. So if you want, the Big Bang would be the circumference here. So when you look at these mergers that occur through the history of the universe, what is really appealing is to realize that even though now we are seeing a couple of billion years back in cosmic history, very soon we are gonna, very soon with upgrades of current detectors, we are gonna push our detection horizons to see almost 10 billion years back in time. And then with next generation detectors, Einstein telescope, Cosmic Explorer, you are essentially seeing all mergers in cosmic history. So that's in just a few decades since the first detection in 2015 to, I guess, in the 2040s, we will be going from the first detection to seeing everything in the universe. And this is from the cosmological perspective very interesting because at present time, we are in a period dominated by dark energy with a small fraction of dark matter. But as you look back on time, these components evolve, dark matter becomes more relevant. So you can understand about the properties of dark energy and dark matter when you are probing the expansion of the universe in a wide redshift range. So I was saying the era of gravitational wave astronomy is here, and we have catalogs now with about 100 events that contain binary black holes, binary neutron stars, and also neutron star black holes. But moreover, we are still taking data, and actually, as of we are observing at this very moment, you can get, if you look at this webpage, you can get the alerts that you can even set to get a message in your phone every time this happens. Sometimes, many times in the middle of the night, unfortunately. But what I just wanted to highlight is that when you look at this website, what you realize is that already in this fourth observing run, we have collected 200 other candidates. We call them candidates because we are still finalizing our catalog. This will come up in the summer, but you see that we are duplicating already the number of events that we have. So at the Niels Bohr Institute, we have a LIGO group, and I will be reporting in this talk some of the work we are doing. So before I get more into the details, I think just to also get the big picture in a bit more concrete numbers. So I like to show this plot, which is the number of detection as a function of time. So we have detected these 100 detections that I was saying. We are in the middle of the fourth observing run. And then on the right, you see what is the equivalent of this in terms of horizon distance. So this is what I was showing in the previous plot, but as a function of total mass of the binary. So our detectors are more or less sensitive depending on the total mass of the system. And you see that at most now, for binaries of a few hundred total solar masses of total mass, you can get to redshift of 1. But when you think of current detectors in the next observing run, we are moving to the regime of thousands of events per year. we are getting close to or passing, in some cases, seeing signals beyond redshift 1. And when you think of next generation detectors, here the green line, this is what I was mentioning before that. That's essentially seeing all compact binaries within the history of the universe. So, yes, please.
X2 stands for the next generation.
Yes.
And A was for advanced LIGO.
Yeah, so A plus is like a new, it's how they call the transition concept between for current LIGO detectors towards next generation detectors. Yeah. It's just a bit, it's essentially, you can see here this sensitivity is using the same arms, but with better technology. So yeah, 05 uses the same, doesn't change that much compared to 04, but then this will be like new detectors with the same arms. And then XG are longer arms. Yeah. So what I hope to get at today is to tell you a bit about doing cosmology with these gravitational waves, and in particular thinking about doing cosmology with the full population of compact binaries. And then in the second part, I want to focus on something that is of great interest to me, which is searching for length gravitational waves and understand how this phenomena appears in this new region. And you have already done so, but just as a reminder, please do ask questions. I prefer that we don't get to the end of my slides, but that you are able to ask throughout the talk. So yeah, don't hesitate to do so. So yeah, so the fact that we can do cosmology with gravitational waves stands on the fact that gravitational waves, we can consider them as standard sirens. And what this means is the following. First, this means that to be a standard siren, you need to understand how the signal is. And we do understand how gravitational waves look like by solving Einstein's field equation. And this, I think, is something that is perhaps seems obvious or trivial for, I assume, this community here that mostly work on gravity. But one needs to think that for most of the other transients in the electromagnetic spectrum, we don't really have like the ability to predict the shape of the signal in a proper way. So that, I think this is something which is special of gravitational waves, the fact that we can predict how the signal looks like in simple terms. And then the second aspect is that we understand how these signals propagate, and in particular, the strain of the gravitational waves is going to scale with the inverse of the luminosity distance, and it also gets some factors from redshift. But what is also very important is that we not only understand the signals, how they are generated, but we also understand our detectors very well. And this is something which is, again, very different from electromagnetic surveys, where it's not so easy always to understand your selection effects. But with gravitational waves, we have the ability of to simulate signals in our detectors and understand how many of those we detect for different parameters. So what this means is that you can have these template banks of millions of different types of waveforms. Here is for different masses, and then you can see like how many of those you detect for different properties, and this allows you to understand what is your sensitivity as a function of the properties of the binary. When you put this together, this means that you can extract cosmological information from the gravitational waves, and in particular, the main two aspects, the main two elements that you want to get is, on the one hand, you want to look at the frequency time evolution of your signal, because that is what gives you a measurement of the mass of how massive is the binary. So from these chirping signals, you get the mass of the signal. And importantly here, for the question of cosmology, we are always sensitive to what we call the detector frame masses, which means that we are only sensitive to the wave that has been stretched by the cosmic expansion. So we cannot access directly the masses of the compact objects, they are always have this factor of Z, which is the redshift. And then once you know the shear mass from or the component masses from the frequency time evolution, you can look at the amplitude, and then that's what gives you information of the luminosity distance. So if you want to do cosmology, essentially with the luminosity distance, you have half of the information. You need some information of redshift, because you have distance. If you have time, then you will get information of redshift. Now, from this luminosity distance, you can test actually many different aspects of cosmology, because the luminosity distance gets imprints from the background cosmology that is going to depend on the different components, dark energy, dark matter, radiation, but also it's going to depend on your assumptions. For example, if your theory of gravity at larger scale is general relativity or not. For here, I will, in the next slides, just focus on standard cosmology. But I wanted to highlight that I've also worked a lot on testing propagation of gravitational waves. What do you have? Okay. Testing, thank you. Testing the gravity through the propagation of gravitational waves. Yeah, well, and we have a recent review on this topic. But as I was saying, from gravitational waves, you get directly the luminosity distance. So if you get information about the redshift of the signal, then you can do cosmology directly. But the key the aspect here is that for that, you need to have some sort of, you need to see where the signal is coming from. So you need to locate your signal within a galaxy. So what this means mostly is that you need to have some sort of counterpart, electromagnetic counterpart. Yes?
So the redshift is given with the electromagnetic counterpart?
Yeah, so
Can you measure the distance?
yeah. Yes, so
Without the electromagnetic counterpart?
yes, yeah, so the distance is something that we get for free from the amplitude of the signal. And then the whole business is how you get information of the redshift. And then when you have, for example, a binary neutron star, if you are lucky enough, when this signal merge is going to meet different sources of radiation, short gamma rays, you're going to have a kilonova as well. All of this radiation is going to propagate. And if you are lucky that the signal is not too far away, actually you can detect this electromagnetic radiation. And that's something that we have done for one of our events. So for this event, this famous event in August of 2017, we observed also light from that signal. And then what this meant is that we were able to look with telescope and identify the host galaxy. And then once you know the host galaxy, you can look, you can get the redshift from the spectra of that galaxy.
The only one so far?
Is the only one, unfortunately. Yes. And that actually, yeah, and well, from that event, that allowed to constrain the local expansion rate of the universe, or H0, which just with one event is not competitive to other measurements, but it was a first step. And of course, the hope is that, because you might know that there is this tensions in when people measure the local expansion rate of the universe with a cosmic microwave background or with local measurements. The hope is that if you accumulate enough of these binary neutron stars, then you will be able to arbitrate this Hubble tension. However, as I was saying, it's unfortunate that from this large catalog of 100 events, we only had 2 other binary neutron stars. Sorry, there were only 2 binary neutron stars. One is the one we have talked, but the other one didn't have a counterpart. It was very far. And also, when we look at the 200 candidates that we have so far, actually 0 are candidates of binary neutron stars. So I think using bright science to do cosmology is beautiful, but so far it seems that we were lucky. We seem to have been lucky with the first one.
Yeah, it's a problem of technology. It's a problem of
Yes, so the issue is that you need to have the signals need to be relatively close, and then the problem is that there are not that many, and also we are not so good at locating where the signal is. So then, if you tell the astronomers, okay, you need to find this in half of the sky, it's difficult for them. And if we take this plot from what I was from before, what you can realize also here is that when you go to total masses of just like a couple of solar masses that will be neutron stars, you are really looking at with binary neutron stars, you're only going to probe the local expansion rate in the near future. So if you want to understand something about the expansion rate of the universe at higher redshifts, you need to have other type of sources, at least in the near future. So this motivates also to think of alternative methods. And one of the things that you can think about is that you realize that here in this formula of the masses, there is some redshift. So actually the masses that we observe, they get some imprint by the expansion of the universe. The question is how you can get it. So if you look at a single event, there is no way in which you can, well, if you look at a binary black hole in a single event, there is no way you can disentangle this degeneracy between the mass and the redshift. However, if you look at all the events that you have, you can try to identify features in the population that will allow you to get information of the redshift. So the cartoon picture of this idea is that you are counting, when you are observing, you are just counting how many events you have at different masses. So you are counting, it seems that maybe at 10 solar masses, there are many more events you count. And then when you do this counting and you identify, okay, there are some features, there might be some peaks. And then you you do this counting in your catalog at different distances. And then what you will find, if you think of the detector frame masses, is that as you look to further distances, all your spectrum is going to be shifted because all your you are getting this factor of 1 plus c. So if you look at how much in this cartoon picture, how much this peak has shifted, this has some information about redshift. And you can ask, for example, if you were to change H naught to make it higher, then this will see the values to the right. If you change omega matter, the amount of dark matter in the local universe, this will change to the other side. So there is some sensitivity to how much, how your masses behave depending on the cosmology. And this is something which is interesting because it's a property of the compact binaries themselves and not of the type of sources. So you can look, you can try to use features in your spectrum from the fact that you will have neutron stars with a peak at around 1.4 solar masses, or you could have use some of the features in the binary black holes, stellar mass binary black holes, or you could even try to look maybe in the future if we discover more massive binaries, this would also be used. And there's been a lot of research recently about this topic. Of course, there is something which is key in this idea, which is that you're looking how the spectrum changes as a function of redshift, but of course the properties of the signals, they might change as well as a function of redshift because the environments in which the binaries form, they change. So one of the keys in this spectral siren method is that you need to be able to disentangle what cosmology is doing from what astrophysics is doing. And the simplified answer here is that the point is that cosmology is always going to be a shift at a given distance of the whole spectrum, while astrophysics is expected to change, to affect masses in different ways. So what you need to do is this becomes sort of a data analysis problem in which you need to disentangle this whole shift of the spectrum from changes in state. And one of the ways of doing this is to try to be agnostic about your what is the shape of your population, and then you can try to reconstruct the shape with some Gaussian process, and then you can infer your cosmology with this Gaussian process that avoids, for example, so here this is a bit exaggerated, but here the intrinsic model is the black line, which is what is a power law peak model. When you analyze this data, this simulated data with this power law peak model, which is the intrinsic model, you recover the cosmology that you have simulated. When you use the Gaussian process, you also recover it. But then if you use, for example, a model which is not good representation of the data, you bias your cosmology, red line. So one avenue to avoid this possible bias of not having the right astrophysical model is to use inference from agnostic models. But to give you a sense of why I'm excited about this method is that when you think of just current detectors with at the sign sensitivity, we are going to be able to detect, measure the expansion rate of the universe at redshift of between 0.5 and 1 with a precision that is going to be better than 10%. This still is not super impressive, but when you think of next generation detectors, and this is, by the way, with 1 year of data, if you accumulate more, this will improve. But when you think of future detectors, you are thinking, you are targeting 2% precision just in a few months, and this is at high redshift. So you can put this in perspective. Just h of c as a function of redshift. The blue is what you would get with 1 month of data in next generation detectors, and this is compared to the dark energy spectroscopic survey. Of course, there will be a bit of some improvements from cosmic surveys, but this is a completely independent way of probing the expansion rate of the universe at high redshift. And you can combine your different methods for cosmology, and you can get improved constraints on the expansion rate. Yes, please.
Since you're quoting Daisy,
Yes.
Can you say also something on equation of state of dark energy, or is it dependent? Like, are you standard siren regardless of that assumption, or?
Yeah. So you can probe the evolving dark energy as well. For that, that happens is what you care most about is actually around redshift of 0.5, because that's more or less when you are transitioning from dark matter domination to dark energy domination, and that and this method is you can do it for extensions of the standard cosmological model. What is unfortunate, I think, well, I mean, we'll see, but with this precision that we will have in this decade, I think we are not gonna be able to say something meaningful. I mean, with this precision, I think it's meaningful, but then also it's a bit later. So I don't know. I'm not so sure of how relevant is gonna be this type of analysis for that question, because I expect other surveys like LSST, for example, and Euclid to be able to give perhaps more answers to that question. Yeah. Yes.
There was also this Niels binary Niels observation from which they also expected to happen.
Yes.
But here you say you can also do it with a black hole population.
Yes.
And which one is more accurate? Or
yeah. So it depends on how many multi-messenger events you have. So you have to think that mostly when you have a multi-messenger event, the error comes essentially from the error in the distance of the gravitational wave, and that's at least 20 to 50%. If you accumulate many of those, you can do your Gaussian law is divide by 1 over the square root of the number of events, and that's your improvement. On the other hand, I mean, when you think of like these future detectors, for example, binary neutron stars which are nearby, they are going to be detected with really high signal to noise. So this means that their error in the luminosity distance will be very small. So you're going to have like very precise measurements then. So one of the things that you can do is you can join. So probably so multi-messenger events, when you accumulate several of those, at least, that will happen eventually. I think we've been a bit unlucky, but eventually it will happen. It will be always better to constrain the local expansion rate of the universe, but because you don't have that many multi-messenger events farther away, I think this spectral siren is better. But the nice, I think, idea is that you can combine both as well. And here I'm quoting this dark sirens, which I should have mentioned before, which is also that you can use electromagnetic information even if you don't have a direct counterpart, because if the localization is very good of your event, then you can look at the galaxies which are within your error volume, and then hopefully if the localization is very good, there will be only a few of them, and then you can statistically say, okay, it must come from one of these galaxies, and you get some notion of the redshift. So actually, with next generation detectors, there will be binary black holes that will be so well constrained that there will be only one galaxy within the localization volume, and they will be effectively as bright sirens. So this is actually the number that I'm quoting here in green. But those only happen at low redshift, so that's why they are constraining better. When you put the two together, you improve the constraints in H0, and then this cuts the other thing. Yeah.
Okay, and in these precision curves that you were showing, there was this optimum sort of at 0.5.
Yes. So that's a combination of the properties of your population and your detector sensitivity. So that's actually, thanks for that question, because I want to stress as well that here, this is data that we are simulating, and then we are making assumptions about how the population of black holes evolve as a function of redshift. So we have some knowledge of how this population is from the observations up to redshift of below 1. But then beyond that, we are extrapolating from what we think are reasonable astrophysical models. But essentially, typical models, they increase as function of redshift until some peak, and then they decrease. And that comes from the fact that if you think that black holes are the end product of stellar evolution, we know very well that the star formation has a peak at around 2 or 2.5, and then it decreases. So you would expect that for binary black holes, something similar will happen. But then actually, this base point is very sensitive to actually where this peak is, and also the sensitivity of your detector. So it depends a bit on both. Yeah. More questions related to cosmology, because I think we're going to shift to lensing. So. Okay. So we've been thinking of these signals that they are propagating for billions of years in the universe, and they are giving us information about the background cosmology, if you want, how the universe is expanding. But of course, the universe is not empty. From time to time, in fact, always, these signals are going to be affected by the gravity of the cosmic structures, and from time to time, they can be heavily affected. it's important that we, as we are also expanding the horizon of our detectors, that we think of including these effects of gravitational lensing. The other thing which is important to also put into context, and again comparing with other transients, is that actually when you think of like light, for example, like fast radio bursts, these transients, they can interact with the intergalactic medium, they interact with the gas. There can be many things that change the signal itself. But actually, when you think of gravitational wave, it's only gravity, it's only gravitational lensing that is going to affect the signals. So if you are thinking of if you are within general relativity and you think you understand how the signal is emitted, and of course there are questions, and I know people work here about environments around the black hole. So you taking that apart, I think if you think you understand how the signal is emitted, actually the only way you can change that signal through the propagation through the universe is by having gravitational lensing. So that's something that is useful, because then when you are looking at the data, if you see deviations, you can try to associate them to this effect. So gravitational lensing is something that is very ubiquitous, and we have really a lot of data now from electromagnetic observations, and it can do very funny things. So for example, when you have good alignment, you can produce multiple images of your distant quasar. You can even distort the shape of the signal, and above all, every distant galaxy that we observe in the universe has some little effect from gravitational lensing. If we want to understand how gravitational lensing affects gravitational waves, essentially what we need to solve is the propagation equation for perturbation, spin-to-fin perturbation in this curved background. Effectively, what this means is that what we are going to want to do is a mapping between the source and the observer through a given lens. And in general, this problem can be quite complicated, but for cosmological setups, actually there are many simplifications that you can do, because typically the distance between the source and the lens and the observer are much larger than the actual size of the lens. So this means that, for example, you can consider your lens to be a thin lens, and also for the typical distances that the wave approaches the lens, then you can think of gravity as being in the weak field regime. So you don't need to consider a strong field effect for most of the cases. So when you have these approximations of weak field gravity and the thin lens approximation, the previous equation, you can translate that you can go to Fourier space, and at the end, solving lensing can be translated into solving what is called the diffraction integral, which essentially accounts for all the possible paths that the wave would take from the source to the observer. So essentially, you are integrating over the time delay that the source will get. You can delay the signal because you are changing the path, and also you can delay the signal because it's feeling the gravitational potential of the lens. And you take into account all the possible paths across your plane of the lens, and that's what's going to give you the general effect. So this is what you need to solve in general, but also there are limits in which you can solve this integral, which are simpler, and in particular, when your exponent is highly oscillatory, you can just solve this integral using the stationary phase approximation. So this is very, it's a standard tool that we use, for example, in quantum mechanics. And then what you realize is that when this is highly oscillatory, so when your frequency is very large, also people call this geometric optics regime. So when you're in geometric optics regime, what happens is that the stationary points of your exponent, so the points where your time delay, the derivative is 0, this is gonna define where you form images. And then from the second derivatives of this time delay, you can get information of how much you are gonna amplify this signal. So you get information of the magnifications. So in this regime of stationary phase approximation, your full diffraction integral simplifies to a sum of different images that can have some magnification. They will in general have some time delay, and they can also have some phases. These phases depend on the solution that you have of the lensing potential and can be of three types. So in general, if you have your source and your lens, you can have images of what is called type 1, which just means that you can just increase or decrease the signal, but you are not changing the shape of the signal. When you have images of type 2, which is when you have this NJ being 1/2, then essentially the physical thing you are doing is you are flipping the image. And then when you have images of type 3, you are flipping the image once and then twice. So this is the phenomenology that you have when you are in this regime of multiple images. And notice that the condition is that you need to have that the time delay between the images times the frequency of the wave has to be larger than 1. And this is something that in the electromagnetic spectrum is almost always satisfied because you have very high frequency signals. However, for gravitational waves, actually, because the wavelength is associated to the orbital separation of the binary, actually your wavelength has a size that can be comparable to the size of the lenses. So it's not always in gravitational wave lensing that you can use this approximation. So, but broadly speaking, there will be these two regimes. One in which you have like big lenses, such as galaxies, and then you will produce multiple images. And then when you have smaller lenses, you will have to solve this diffraction integral. And then in that case, you would expect to have distortions in the shape of the signal. So one of the things which it's I think appealing about studying gravitational lensing in general is that because you are magnifying the signals, it gives you a way of observing further. So if you think, for example, of just our current detectors, O4 sensitivity, if you have a magnification of 10, you are kind of like pushing your detectors to be more sensitive than O5. If you have a magnification of 100, you can see things much further. And I think the other aspect that is exciting of gravitational lensing is that although we have not observed it yet, it's something that it's expected to occur very soon, because the rates, at least for this strong lensing by galaxies, is that we expect 1 in every 1,000 or every 10,000 to be strongly lensed. So that's something that we expect in the near future, and we are actively searching for it. But just to give you an example of one of the things that you could, one of the ways in which you could use this expansion of the horizon could be to detect new populations. So, for example, you could think of this is the number density of some population of black holes as a function of redshift. You have this is, by the way, what I was saying before, that the merger rate increases as a function of redshift as a peak, and then it decreases. And this is the standard thing that we expect for the binaries that we are observed. But there could be other formation mechanisms. For example, if you have like what people call this population 3 stars that may collapse directly to form black holes in the early universe, this might be a very different spectrum. And then when you think of from this population of thin binaries, how many of them you detect with current detectors, what you realize is that, I mean, from the 100,000 that merge every year in the universe, you are only going to detect 1,500. But then from all of these events that you detect, a fraction of them will be lens, and we might be able to see those. But I think what is interesting is that it could be that you have other populations that you are not seeing. You will have no detection without lensing, and then lensing essentially brings them back to your horizon. What this means as well is that if you have a signal that is highly magnified, then it might look as an outlier in your population. So what happens is that if, as I was telling you, what we infer is the redshifted masses and the luminosity distance. But if you magnify an event, essentially what you are doing is that you are thinking that your event is closer, and then if you think that your event is closer, when you take the detector frame mass, you will think that the source mass is bigger. So if you have, for example, this is the distribution from simulated events in luminosity distance and source frame masses. If you take one event here and you magnify it by 30, then you will move it to this cross here. And then what might happen is that if you don't, you will say, okay, this is quite a heavy event to be at this distance. Of course, this is complicated because to identify lens events in this way, you need to know very well what is the astrophysical population. So it's not so trivial as it is, but there might be events that are lens that appear in this way. The other thing, which is also important to see connections with other aspects of gravitational wave astronomy, is that because lensing can distort the signals, you may be testing, looking for deviations of test of gravity, and you might be finding things and say, okay, this is violating gravity, but indeed this is just a reflection of lensing. And there are known degeneracies. And for example, there is one, if you are looking for modified dispersion relations. So for example, if you have something that you have a mass for your graviton, or you have some other terms in your dispersion relations, this effectively is going to change the phase evolution of your gravitational wave. But lensing also can have some phases that can be degenerate in this case. So it's important. So I think there are also connections there with that relevant. The other aspect, which I think is very interesting, is that because of these wavelengths being having astrophysical sizes, as I was saying, they can be comparable to the size of some of the lenses. So typically, a gravitational wave has a wave of 1,000 kilometers if you have 10 solar masses. But if you have bigger, more massive objects, you could have larger wavelength. But what this means is that your gravitational waves, they may be lensed by compact lenses, such as primordial black holes or intermediate mass black holes. And those compact lenses can produce quite high distortions in the waveform. So, for example, if you have some lens of 1,000 solar masses, then this will give you time delays between the images of 40 milliseconds, and then you will get things like the orange line, which is quite different from the unlensed signal, which is the blue one. So one of the things that when you are looking for distortions of lensing, you are putting constraints on this possibility of having these compact lenses in the universe. So when I say we, is because I'm part of I was saying before of the LIGO collaboration. We are searching for these lens events in our data. We have not found it so far. So we have looked for repeated shifts. So we look at pairs of events and ask the question, can this be actually the same event? And we also look for this kind of distortions that I was showing before, but we haven't found anything yet, which is, on the other hand, not surprising given the rates that I was telling you before. But still, from this non-observation, you can always put constraints. And what this means is because lensing is giving you this extra horizon. I mean, you're expanding a bit your horizon. It means that you can put a bit more constraints at higher redshift. So this is the constraints on the merger rate without lensing is the gray line, and then when you include lensing, this will be this green. So you improve a bit just by including lensing, which is interesting. And we also put constraints, for example, on the amount of primordial black holes that could be in the universe. I don't have here it is in the slide, but that's something that we do. However, I think there is something which is important. It's an important caveat, which is that when we are at the moment, when we are doing our searches, we are using, we do our searches using templates. So we use models for gravitational waves that we generate from numerical relativity simulation. And those templates have not been lensed. So what this means is that we are using a given model to filter our data. However, and this is fine if the distortion that you have from lensing, and this is, by the way, the same for modified gravity. If the distortion that lensing is producing is very large, actually the templates that we have might be not efficient enough to detect this signal. And this is work that a PhD student in the group has done. For example, when you look at the this false alarm rate is the kind of the statistic that we use to determine if an event is real or not. And we want the false alarm rate to be at least smaller than 1 in every 6 months. But you see that for certain masses of the lenses and certain impact parameters, actually you can lensing can make that the matching with the templates is very bad. So actually, we are really not that sensitive to these match rates in here. So that's something that is a caveat that we should take into account. So I think we should be, yes, please.
How much amount of work would be to sketch the catalog, including the
Yes, so that's a great question. So actually, the searches can be very expensive because you are doing checking your data with millions of templates. However, what we are thinking about is that there could be, it's only a fraction of the parameter space that we would need to extend, and that could be helpful. And also, what we are hoping is that we are exploring, because this work was done for a point lens, but you could have other type of lenses. But we are finding that actually there are simplified models in which you can describe different lenses. So we are hoping that with some simplified model, we in a small region of the parameter space, that could be enough to cover this. The other way actually would be that we are also thinking about is that these results is when you are doing, you are searching in your data using templates, but we also searching the data in an unmodeled way, just by looking at the excess of signal that is correlated between the detectors. So you could also try to look for that. But the problem of that is that it's only really working well when you have more massive events, which are higher signal to noise. So it's not so easy for lower mass events, because those actually, they are not really above the noise. It's only when you filter them for a long time that you get the signal. So that could be tricky for a smaller mass, but maybe perhaps for the bigger mass, it's already enough with what is being done. So that's something that we are investigating as well.
Let me just clarify.
Yes,
I
please.
understood. So this work, you said you have a point lens.
Yes.
So you actually know, like, if you know the properties of the signal from the binary black hole,
Yeah.
how the signal is after its lens. Like,
Yes.
you've got the full waveform.
Yes.
Okay.
Yes. So that's also one of the things which I think is appealing of searching for lensing distortions, as compared, for example, for some other, like modified gravity in general, is that actually lensing, makes very concrete predictions that you can look for. So at least if you have these compact lenses, it's typically that you have two images which are interfering with each other, and that's something that you can model you understand how to model it. Yeah.
But
Yes.
if you were to produce templates
Yes.
or lens models or lens waveforms, you have additional parameters.
Yes.
Right. So
Yeah.
you have probably the distance and the mass of the lens.
So in this case of compact lenses, it's essentially the mass of the lens and the impact parameters. So how aligned is the source and the lens? These are the additional parameters that you have essentially, because your lens is in this simple model is just with the mass you can describe it. Well, the distance you already have. I mean, distance is always there. Sorry, you mean the distance to the lens? Sorry, yes. Yeah, this lens mass, sorry, is the it has the redshifted lens mass, so the redshift goes there. So yeah, so this lens mass also has the factor of 1 plus c of the lens.
But it can be sort of combined.
Yes, yeah, because in the same way that you have the degeneracy from the gravitational waves, I mean, this is just a fact that because gravity is scale free, so it's the same for gravitational waves, it's the same for the lenses. Sorry, you wanted to ask something?
No, wait.
Okay, yeah, so I think we are at the end. I just wanted to flash something which we are actually, I think it's as well exciting that we are thinking about, which is that when you are making this mapping between source and the observer, between the source plane and the image plane, there are actually certain source positions where you would infer that the magnification of the images is infinite, and those are singularities of the mapping between the lens and the image. And this is, I mean, when you look into like in a swimming pool and then you see like these bright spots, this is just where you are focusing the light, and it's essentially the same effect. But what is interesting is that actually when you in nature, we don't have these infinite magnifications, and the way that you regularize them within gravitational waves is by the fact actually that your wavelength is finite and you have diffraction around those points. So we have been studying how would be the lensing, in particular for a gravitational wave when you approach to acoustic. I mean, lensing by caustic is a very like well-studied field in electromagnetic gravitational waves. But the interesting thing is that for gravitational waves, I mean, it will imply like that you have highly magnified overlapping signals, and it also implies that you may have like these interesting diffraction patterns that could translate, for example, into very distorted waveforms. So this is just, for example, if you are approaching what we call a caustic, which is just this point here this is the source plane magnification, this is the image plane magnification. When you approach this cast, you can produce 3 images that they can overlap with each other. So I think this is interesting. We have some work that will be probably on the archive later this week that I think is exciting. And I have a bunch of other things, but I think I'm gonna just jump to the, well, maybe just mention this, that actually a group of students in our group, they got together for a week in a summer house, and they actually computed the corrections of what I was telling you all so far is lensing in the weak field limit. But when your lens is a black hole, some of the waves can be absorbed by the black hole, and also some of the waves will be reflected by the black hole. And what this means is that lensing in that situation also becomes polarization dependent. So they have a recent paper about that, and I think it's very interesting. Yeah, but let me just finish by saying that I think gravitational waves are going to open like a new way of exploring the universe, and in particular, I think from the population of binary black holes, we are going to have a solid way of measuring the expansion rate of the universe. And I think also in parallel, these lens gravitational waves are will allow us to observe a new population of black holes and also probe dark matter substructures. Thank you for being here. Sorry that I took that moment.
Yeah.
Ask a question about actually the lacking the strong field effect. So you mentioned at some point that the thing that we care the most about is lensing, which I guess that's like the first order effect.
Yes.
But how much do we expect this kind of behavior to change this strong field behavior to change the things that we actually see? Like, does it happen a lot in a lot of the signals? Or?
Yes. So not so much because for a strong field to be relevant, you need to be actually the source needs to be quite close to the lens, so that the chances that the wave passes very close are high enough. So in general, actually, like lensing, one of the scales of lensing is the Einstein radius, that tells you like the scale at which you have you will produce multiple images, and that for a lens at cosmological scale is orders of magnitude bigger than the Schwarzschild radius. So you will need to have like very good alignment. However, there are situations that that motivate this kind of study, because if you, for example, have like a binary which is in a active galactic nuclei, so in the disk of a supermassive black hole, then actually there are studies that say that the binaries will tend to form like what they call these migration traps, which are only tens to hundreds of Schwarzschild radii from the bigger black hole. So in those situations, this kind of phenomenon might be relevant, because astrophysically you're already putting the system in an alignment. But in general, if you think of just a random signal and a random black hole, I mean the chances of lensing in general are low, and if you need to have bigger alignment for this, will be even more unlikely.
And is it something similar for the lens by caustics? Like you also need to have very good alignment?
No, it depends, because actually, when in that case the caustics will be at the scale of the Einstein radius. So that that's more likely. And there is also the observational bias that you have to have you are more likely to observe things which have been lensed, which have been magnified, because lensing is more probable at high redshift. So then if you magnify them, you have some selection bias toward high magnification, which would occur near a caustic.
Maybe on this, so
Yes.
this calculation has been done for a Schwarzschild black hole or a rotating one? Because
Yeah, so this work in particular is for a Schwarzschild black hole.
Mhm.
There are other groups that have done it, have studied this for Kerr black hole, but I guess what is nice of this work is that they actually look at the waveform itself. Like, so when you think of lensing in a strong field, actually, I mean, this is essentially the problem of the scattering of a
Yeah,
wave with a
exactly.
black hole that has been
and I
studied.
was thinking of
perturbation.
rotating, because in this case you could have super radiance.
Yeah. So, but I think people are trying to translate what has been already understood from like black hole perturbation of Kerr black holes to this context. But I think that there is still work to be there, and perhaps some of these effects can be explored. I don't think they have been fully explored.
If you enjoyed the video, like and subscribe.